In this video, we're going to introduce logarithmic properties and models. So it turns out there are three logarithmic properties that are going to be very helpful to us as we solve exponential and logarithmic equations that we have not been able to solve before. So let's talk about what those properties are and verify that they really are true. So the first one says that the log base a of the product of x and y is the same thing as the log base a of x plus the log base a of y. And again, if you think about what logarithms are, this is not a very surprising result. Logarithms are exponents. All this statement is saying is that when you multiply, you add exponents. Literally all that statement says. Means that you probably guess what the next property is. The log of base a of x over y is the log base a of x minus log base a of y. And again, all this is saying is that when you divide, you subtract exponents. The third one says log base a of x to the r power is the same thing as r times log base a of x. And again, if log base a of x is giving you an exponent, again, all this is saying is that if you raise an exponent, something with an exponent, to another exponent, you multiply the exponents together. So these are basically your laws of exponents just written in logarithmic form. Let's verify that these are true. So for convenience sake, let's say we have p is equal to log base a of x and q is equal to log base a of y. Rewriting these in equivalent exponential form, the first one is x equals a to the p, the second one is y equals a to the q. What happens when we multiply x and y together? Well, x times y will be a to the p times a to the q. Here's what I was mentioning when we add our exponents. That's the same thing as saying xy is equal to a to the p plus q. This is an exponential equation. We can rewrite it in equivalent logarithmic form. Log base a of xy is p plus q. And we said that the p was log base a of x and the q is log base a of y. So this verifies our first property. Verifying the second property is very similar. Let's first start with the quotient of x and y. That will be the same thing as a to the p over a to the q. When we divide, we subtract the exponents, so we get x over y is equal to a to the p minus q. Rewrite in equivalent exponential form, we get log base a of x over y equals p minus q. And we said p was log base a of x and q is log base a of y. So that verifies our second property. Let's do the last one. X to the r. Well, that'll be a to the p raised to the r power. When we have one thing with an exponent raised to another exponent, we multiply our exponents together. So this is x to the r as a to the rp. Rewrite in equivalent logarithmic form. That gives us log base a of x to the r as r times p. And one more time, p is log base a of x. So we verified our three log properties, and these are the log properties. There are some other things that are very tempting that you do not do. Those tempting things are these three. These are not log properties. Logarithms do not break up over sums. Logarithms do not break up over differences. These are not valid properties. Do not try to use them. All right, so let's see if we can do valid log properties and simplify some things. The first one's asking us to simplify log base 3 of 9x root y. Well, the inside is 9 times x times root y, so that's a product. We can break products up as sums, so we get log base 3 of 9 plus log base 3 of x plus log base 3 of y to the 1/2, rewriting this as an equivalent exponent. That exponent, that 1/2 exponent, we can bring down in front, so we get log base 3 of 9 plus log base 3 of x plus 1/2 log base 3 of y. These two, there's not a lot more simplifying we can do because we have a single x on the inside, a single y on the inside. However, 9 is the same thing as 3 squared, so log base 3 of 9 is simply 2. So finishing this off, we get 2 plus log base 3 of x plus 1/2 log base 3 of y. The second part asks us to simplify log of x squared over 10,000 y cubed. So first, we have a quotient. So I can break that up as a difference. We get log of x squared minus log of 10,000 y cubed. We now have a product in that second term. We can rewrite the product as the sum of the logs. So we get log of a 10,000 plus log of y cubed. And we need to make sure we put parentheses around that whole thing because it's the log of this is what's being subtracted. So I need to do minus each of the individual logs. For your first term, we've got a 2 as an exponent for the x, so we can bring it down in front. So we get 2 log of x. Oh, for the third one, I've missed a 3. This 3 should be down. There should be a 3 log x here. Not just a simple, or excuse me, a 3 log y, not just a log y. There should be a 3 right here in front. Okay? So we should have 2 log of x minus log of 10 to the 4th. We can rewrite this as an exponent, 10 to the 4th. 10,000 is the same thing as 10 to the 4th. But this should be a 3 log y. Remembering now that log all by itself is common log, or log base 10, that second log just simplifies to 4. So our final answer should be 2 log x minus 4 minus 3 log y. And again, I've missed that 3 here as the exponent because this 3 should have come down in front. For the last one here, we have natural log of the 4th root of e cubed x over z squared. First thing we'll do is rewrite the radical as an exponent. Write it to the 1/4 power. We can bring that exponent down in front. We get 1/4 natural log of e cubed x over z squared. This is now a quotient. We can write the quotient as a difference, so we'll get 1/4 times the quantity log of e cubed x minus log of z squared. This here is now a product. So we get 1/4 natural log of e cubed plus natural log of x for that first term. We have a z squared in the second term, so we can bring the 2 down in front. And get minus 2 natural log of z. Finally, remembering that natural log is log base e, natural log of e cubed is just 3. So we get 1/4 times 3 plus natural log of x minus 2 natural log of z. Well, besides breaking logs apart, we can also put them back together. So that's what this example is asking us to do, is to combine these back into a single logarithm. This last one here should also have a base 2 on it. So it should be log base 2 of x minus 3 log base 2 of y plus 1/3 log base 2 of z. Actually wanted to, honest to goodness, put all 3 of them back together as a single logarithm. If I don't have the same base, I can't put them back together. So there should be a log base 2 here. So log base 2 of x minus 3 log base 2 of y plus 1/3 log base 2 of z. First thing I can do is bring the constants that are in front up as exponents. So in the second term, we get log base 2 of y cubed. And in the third term, we get log what should be base 2 of z to the 1/3. I have a difference of logs in the first two terms, so I can rewrite that as a quotient as log base 2 of x over y cubed plus log of base 2 again, z to the 1/3. Now I have a product because we can rewrite it as a product because we have a sum. So we can rewrite this as a final answer of log base 2 of x z to the 1/3 over y cubed. In the second one, do the same kind of process. I have a 5 in front of the natural log of x, so I can bring that up as natural log of x to the 5th. We have a 2 in front of the natural log of y, so we can bring that as a natural log of y squared. And I'm going to go left to right in order here to rewrite this and make sure I don't get things messed up. The first two I can rewrite as a quotient and get log of 7 over x to the 5th, and then I still have a minus log of y squared. That again is a quotient, so that becomes 4 times natural log of 7 over x to the 5th times y squared. Both of those will be in the denominator. And then finally I've got a 4 out in front of this natural log, so I can bring it up as a 4th power for our final answer of natural log of 7 over x to the 5th y squared, all of that raised to the 4th power. All right, so if we want to solve an equation like 4 to the x equals 11, we know that we can rewrite this as an equivalent log form and basically get the solution of log base 4 of 11. That's really, really hard to see what that is, and it's difficult to approximate a solution. And even if you do have a calculator, log base 4 probably is not a button on your calculator. You probably have common log, or log base 10, or natural log, log base e. So if we want to compute something log base 4 of 11, we're going to need to use the change of base formula. Change of base formula says that I can take log base a of x and change it to any other log base c for any other c by writing this as log base c of x over log base c of a. Just like before with the properties, let's see if we can verify this particular one. Again, let's say that log base a of x is p. Rewrite it in its equivalent exponential form as a to the p equals x. In that second equation, let's take the log base c now of both sides to get us log base c of a to the p equals log base c of x. We can bring the p down in front, so we have p log base c of a equals log base c of x. Solve for p by dividing both sides by log base c of x. And now p was the same thing as log base a of x. So here is our change of base formula. Usually, if we want to use change of base formula, we use natural log or common log because those are the buttons. Any base will do, but we want to try to use this to approximate things, so we're going to use either common or natural log to rewrite. So let's do that with these three. The first one asks us to evaluate log base 8 of 23. Certainly we don't easily see 23 as a power of 8. So we can use our change of base formula. This is the same thing as log of 23 over log base 8. Here I'm using common log. I can type both of those into my calculator and get about 1.5-ish. And there's what the syntax would look like in your calculator in that case. We can do the same thing for the second one. The second one asks us to evaluate log base 1/3 of 12. In this case, I use natural log. Again, it doesn't matter if you use natural or common log. We would have natural log of 12 over natural log of 1/3, and type that into the calculator. We'll get negative 2.2619. And again, there's what the calculator syntax would look like. Finally, we're going to do log base pi of e. Again, we could use any log base with what we want, but since we have an e in here, we definitely want to use a natural log because that will simplify to just 1 when we do natural log of e. And then again, if we put this in the calculator, we can do natural log of pi, and we get about 0.8736.